you to find the derivative dy dx, how would you probably do both of these? Implicit differentiation. So you just start taking derivatives. 2x, we don't need a dx with x. We have to take the derivative with respect to x. Derivative of x with respect to x is just 1. So it's just 2x. What do we have to do on that second? This product rule. Left, d right, plus right, d left. I usually keep the -3 as part of the left. So I do that to be careful, make sure both of them end up negative. So far, that piece plus a dy dx equals 0. Let all the dy dx terms on the side. Dy dx terms on the other one. Does not matter which side you go to. Options. 8y minus 3x, leaving them on that side. Moving the 2x and the 3y over. I did a lot in that step, so I'm going to pause for just a second. Any questions about anything there? And then divide by the 8y minus 3x to get y dx. Any questions about that one? The next one. Product rule. Left d right plus right d left. So I get x times dy over dx equals negative y. Divide by the x. This skill is going to come in handy today with the word problem types that we're going to be doing today. Pull those in. Today we're going to be looking at a special type of word problem called related rates. A related rate problem is one where there are two rates that are related somehow. So two velocities or two speeds that are somehow related. In that, we're going to be looking at different differentials, like dy over dt and dx over dt and some things like that. So before we actually start the problems, I want to do a little bit of calculus behind it. So I have x times y equals 4. Now I just did this derivative with respect to x. I found dy over dx. I don't want to find dy over dx. I want to find it with respect to time, which is what most rates are. Most rates are miles per hour or feet per second or gallons per hour. So I want to find this as a rate in terms of time. So instead of taking the derivative dy dx, I'm going to take the derivative with respect to t. Now what that means is now every variable is like a y. So, show you how that works. I'm going to do left, d right, except this time it's dy over dt instead of dy over dx. So far it feels completely identical to what we did in the lower here. Plus, right, d left. Well, this time, dx also gets a dx dt. And that's because it's not with respect to x anymore. So change in x over change in x is 1. And that's why we never write that down. Change in x over change in t is probably not 1. So we need to write that down. So then, after I do that derivative, it asks me some questions. Find dy dt when x is 8, given that dx dt is 10. So we'll see if I can do that. See if I can be successful on that. So it tells me that dx dt is 10. It tells me x is 8. and I want to find dy dt. What is my gap that I don't know? I don't know y. If I have an x, can't I always find a y? Where do you do that at? The original. X times y equals 4. So if x is 8, what would y have to be? Half. So I'm going to agree. Divide 8 with half. So I get 8 dy over dt equals -5. So dy over dt is -5/8. Very similar question, except it gives me different information. My derivative is the same, so 3/5 out it's x dy over dt plus y dx over dt. Find dx dt when x is 1 and dy dt is 6. -6. What would y be if x is 1? So how do you find that? And how'd you get that? Plug into the original. So I know that x times y equals 4. If x is 1, y would have to be 4. I'll let you.
Yeah, you write it down. I don't know.
So you see how I got the derivative? The calculus part's good. So from here to here, I plugged in what they gave me. What they didn't give me was a y. But they gave me an x. So if I have an x, I should be able to find a y. What do you think? Now?
Yeah.
Now I just want to get dx dt by itself. So we get 4 dx over dt equals 6. So dx over dt equals 6/4 or 3/2. Now most teachers would skip this slide. It's not a word problem, and we would kind of skip into the word problems. But I've found this to be beneficial, kind of figuring out what that whole dx means. It is a change of x over time. So we're going to be working with that today. You do not have to write these steps down there at the top of your homework. But I do want to make through them. So in the real world, the rate of change on things changing often affects one another item's rate of change, how another item's rate of change works. For example, if you fill up a glass of water, the rate at which the volume changes affects the rate at which the height changes, and vice versa. Those are related. In calculus, these intertwined rates are called related rates. So we're going to look at steps for solving a related rates problem. It is a word problem. So as you can imagine, the first thing we're going to do is read the problem, identify what we're trying to find, draw a picture, label variables. On the picture, put constants down on the picture. Don't put other quantities down on the picture, just constants. Otherwise, label variables as variables. If something's going to change, leave it as a variable. Beside the picture, identify rates as derivatives. Caution, if something is growing, what do you know about the derivative? It's positive, and if something is decreasing or shrinking, then the rate would be negative. So we're going to have to keep that in mind. Find an equation that ties all the variables and constants together. Find the derivative using implicit differentiation for all variables. So even if it's an x, you're going to use implicit differentiation because our derivative will be in terms of time. Now, on the last slide, I used the x dt notation just to overemphasize that it's dx over dt. If you like prime notation, you can still use prime notation. You can still call it x prime, you can still call it y prime, you can still do that as you did before. You just now know that it's with respect to time. Using the other notation, the only thing that's good about it is it'll kind of help you with units a little bit. As you saw on that first day when we were breaking down what dV over dt meant, or dV over dr meant, you know that the change in volume over change in time, and so you would know what units to put. Other than that, there's no benefit to either notation. Plug in the numbers for all variables except for what you're trying to find and solve for what you are trying to find. So we're going to start with one that's not too terrible. Of course, just like optimization or with any word problem, these could be as easy as this one. They could be as hard as the cost problem on optimization. It's a word problem like any other. So, however, I don't know. I like related rates better than optimization. You can judge for yourself later. A spherical balloon is being filled with air such that when the radius is 2 feet, it is increasing at a rate of 1/6 foot per minute. How fast is the volume change? This is probably my favorite section of calculus. Before I start, draw a picture, label variables, find an equation, all of those things I would do with a word problem. Really, there's only one variable or two variables that I see here, which is nice. I don't have to do any secondary equations. I just have a volume of a balloon. And I have a radius. Is the radius changing? Yes. So ignore the 2 for now. Don't put it on your picture. It will confuse you if you put a changing number on your picture. So don't put a number that's changing on your picture. We'll deal with it in the equation. So let's start to think of what we know and what we want to know. It says, how fast is the volume changing? So what variable am I wanting to find? Rate of change of the volume, right? What variable would the rate of change of the volume be? The derivative of volume. So you could call it b prime, or you could call it ddt. That's my question. How fast is the volume changing? So I'm going to mental note. That's what I'm looking for. What do I know? I know the rate at which the radius is changing. And if you didn't know for sure that that was a radius rate, feet per minute is a big hint. Those units will really help you out. Obviously, that's not a rate of change of volume. It would be cubic feet per minute, correct? So it's feet per minute. So I know dr over dt is 1/6 foot per minute. And I'm going to go ahead and put when r equals 2. The rate of change of the radius may change as the balloon gets bigger. It may take it longer to fill up or harder to fill up as it gets bigger. That's what I know. What is an equation that relates volume and radius? Almost a silly question, but volume of a sphere to the radius. Is there an equation with volume and radius as variables? The volume equation or something. If you don't know it, your calculus helper will be helpful on these problems. Sphere is one I would memorize. Are they in there somewhere? Oh, good. So if you see the little volume section, you'll find it. Find a cone, a sphere. cylinder. All others, they will probably give you the volume of, except that, well, the only other thing's a box. You would probably need to know the volume of a box. Other than that, they'll give you the equation for those. Those three are the only thing you'll need to know. Take the derivative implicitly. Don't plug anything in except for constants. And we don't have any constants. The balloon is changing. Everything in the balloon is changing. So just take the derivative as it sits. Thank you. So what is the derivative of volume? 4 pi r squared. Any questions about that? I'm wrong, by the way. Where? Every variable needs what? Remember, since I'm not taking the derivative with respect to the radius, I have to have that dRdt. But that's good news, because do I know dRdt? Do I know r? Plug it all in, find ddt.
That's when we cancel in them.
Right, after you already get the derivative. Why would you not want to plug in before you take the derivative? Say I plugged in the 2 for radius at the beginning. What would the derivative be? 0, because we have all constants. And that's not what you're looking for, obviously. It's changing. So you don't want to plug in constants until you're finished. Is the radius, and I should have asked this when I wrote it down, but is the radius increasing or decreasing? Increasing. And so it is a positive 1/6. I wrote it down as a positive, but mental note, always think about whether you're increasing or decreasing. 16 pi over 6 or 8 pi over 3. Since these are word problems, never leave that without a unit. What would my units be? That's where this notation comes really handy. You'll what would units on volume be and what would units on time be. So we have any questions so far? A 5-meter ladder is leaning against a wall. It begins sliding down the wall so that the bottom of the ladder is sliding away from the wall. How fast is the ladder sliding down the wall when the foot of the ladder is 4 meters from the wall and the foot of the ladder is moving away at 2 meters per second? Okay, so what do we know? Ladder's 5 meters long. Is that ever going to change? So I feel comfortable going ahead and putting it on my picture. That quantity will never change. That is very different from other variables on a picture that will change. What are the 2 variables on the picture that will change? The height and the distance, right? You can call those x and y, you can call them h and l, you can call them whatever you want. It doesn't matter what variables you use. Those distances will change. So now based on that picture, what do I want to know and what do I know?
It's moving at 2 meters.
What?
The ladder's sliding down.
Okay, so the ladder, the foot of the ladder is moving away from the wall at 2 meters per second, right? So which variable is that? X. So dx over dt is 2. Now, positive or negative? Well, that distance is increasing, correct? So that's a positive value. I want to know dy dt. When the ladder is 4 meters away from the wall, is that a constant? No, that's still a variable, but we're going to put that kind of here. When the foot of the ladder, so x is 4. Okay. So this is half the battle, finding out what you know and what you want to know. You don't have to do this before you write the equation. Write the equation first and then you'll label variables, but it's handy to have this thought process going. What equation would relate x and y to each other? Pythagorean theorem? X squared plus y squared equals 25. Now, if you had forgotten to put a 5 there, and you had left it as a variable, the problem would look much more complicated. It would look like you had 3 variables going on. As long as you recognize that dc dt was 0 because the ladder's not changing, you'd be okay. But that would be something else you'd have to think about if you hadn't thought to put the 5 here. So I'm going to implicitly differentiate. So I get 2x dx over dt plus 2y dy over dt equals 0.
Plug in 2.
Okay, yes and yes. Plug in 2 for dx dt, plug in 4 for x. I'm trying to find dy dt. What's the problem? They didn't tell me why. And so at first glance, that sounds like a problem. But if we have an x, don't we always have a y? So here's where I'm going to go label my picture a little bit more. If x is 4, now I wouldn't do this at the beginning because you'd think they were constants. But if x is 4 and y is 5, what is 3? 3. I said that wrong, but yes, 3. Everyone agree? Or I could have solved the equation. 4 squared plus y squared equals 25. 25 minus 16 is 9. Square root of 9 is 30. Either way, you can't find that other variable y. 16 plus 6 dy dt, 0. 6 dy dt, negative 16. Negative 8 thirds units.
Meters.
Meters. dy, y was in meters. T is in seconds. Now, why is it negative? Because it was falling down. So now, as we answer the question, we have to keep that in mind that that's 5 is negative. So the question actually asks, how fast is the ladder sliding down the wall? Would you agree that a perfectly good answer is the ladder is sliding down at negative 8 thirds meters per second, at positive 8 thirds meters per second? But that's a perfectly good answer to that question. So the negative, remember, it just tells us a direction. One word of caution. Be careful in how you answer. The way I was writing at first, not that the negative would actually have been wrong. Someone tell me why. Because it would be a double negative. Because I said it was sliding down. At a negative, that would make positive. So be careful about that if you are using words. You probably will want to use a positive value. The problems you will want to star this one in your notes to come up on AP. if you don't pay attention to these will plague you for a while. They come up a lot on your AP packet. There are cones on there. There are cones on this worksheet, and there are cones on your second related rates worksheet that we will work on. I did tell you this is the last new lesson in Unit 4, didn't I? This is the last new lesson in Unit 4. So what that means is we're spending from now until Thanksgiving working on related rates. So you're going to see lots of cone problems. So star this one in your notes. It's a tough one. At first. Once you do a few, they get easy. A few years ago, we were working a problem like this, and one of my students said, "They don't make takes that are in the shape of cones, Miss King." So I went and found a picture of one, just in case. Kind of functions as a funnel. Water is pouring into a conical cistern at a rate of 8 cubic feet per minute. The height of the cistern is 12 feet. Your radius of the opening is 6 feet. How fast is the water level rising when the water is 4 feet deep? Okay, so let's draw a picture. I kind of have a picture here drawn, but I just have cone drawn. What's happening in that cone is that we have water filling it up, right? This is our concern, right? It's where the water is. It's not the cone itself. It's the water. So now let's talk about some variables. We have the height of the water. We have the radius of the water level, right? Are both of those quantities changing? They are, because as the cone gets bigger, won't the radius get wider? So both the radius and the height are changing quantities. So do not call them 6 and 12. They are not 6 and 12. That's the height of the entire cone, right? So keep that in mind. Any questions so far? What do I know? What do I want to know?
The radius of the whole thing is 6.
Okay, I know the radius of the whole cone is 6. I'm not sure how that's going to help me at this point, but I do know that.
And the volume of the cone is 1/3.
Okay, so okay, that's the equation. So he's kind of giving us an idea of what we're putting into the equation. What other variables do we have?
I was coming at velocity.
Okay, the 8 cubic feet per minute is some kind of rate. Even if you couldn't figure out from the wording of the problem what kind of rate that was, units are huge there, right? It's a rate of the volume. It has to be because it's cubic feet per minute. So really pay attention to units, and understanding of those units is very important for related rates. So dV over dt is 8 cubic feet per minute. And it is pouring in, so the volume is increasing, so that is a positive value. What do I want to know? That's what. So did everyone agree? I want to know dH dt when the water is 4 feet deep. There are 2 ways to work this problem. There's a smart way and a long way. As with most word problems, there are. Before I start working, I'm going to brainstorm a little. If you don't do that, this problem will be much more difficult. Not impossible, but much more difficult. And I'll show you what I mean by that as we work. What is missing in my variables that I have labeled there. dr dt. I don't know dr dt. Everyone agree? I have too many variables. Now, you can just work it and work with that at the end. Or you could use some skills from optimization and look for a secondary equation to simplify your life.
Would that be like Thompson's?
Yes. Would you agree that in any cone, all the way up, the radius and the height are proportional because you have similar triangles? So I could side note at this point, I would do this with every cone problem that you do. Now, I say this now, there is a cone problem that's a real AP problem where they give you dr dt. Well, you wouldn't want to do this on that one. You could, but you wouldn't want to because you have dr dt. Plug it in, done, move on your way. But if you don't have dr dt, this would create a problem in your work. It's not saying it's impossible to find it. I will tell you later how you can find it, but it would be complicated. So I'm going to say, well, r over h is in the proportion 6 over 12. And so doesn't that mean r is 6 plus h? Or I could rewrite that and get h is 6 r, which is 2. So either way you wanted to do that, you could solve for either variable. Now, time out. Which one do I want to stay in my equation?
R equals half H.
That's what I want, right? Why do I want r equals 1/2 h?
It's a variable we don't know.
It's the variable we don't know, but don't I want the h dt? So I'm going to leave h in my equation. Does that make sense? Or why I really would like to leave h. Again, if I don't, it's not the end of the world. We can recover later, but it's the easiest way. So if you notice that, I'm going to go, well, r is, okay, if I reduce that to a half, r is 1/2 h. So my volume equation for this particular cone is 1/3 pi times 1/2 h squared times h. Could you easily see a problem where they ask for the rate change of the radius? So you would do that a little differently, but very similar thought process. As with any calculus problem, first do some algebra to simplify your life. I could take the derivative at any point along here, but what else could I do? What's one more step I could do to really simplify my life? Pi over 12 h cubed. Pi over 12 is just a constant, correct? So dv dt is 3 pi over 12. You could go ahead and reduce that. H squared times dh dt. And now I think I know all my variables. Let's find out. I know dv dt was 8. Is that right?
Mm-hmm.
Go ahead and write that as pi over 4. Do I know h? Yeah. Now, is there a possibility that they could have r instead of h? Yeah, but I have an equation I could have found the other one using my similarity. 16 divided by 4 is 4 pi. So 8 divided by 4 pi. Be careful if you ever do type that in your calculator. Either use your fraction bar or the system at the bottom. And what would my units be on that since it's dh over dt? Feet per minute? So what does that mean? The water level is rising at 8 over 4 pi feet per minute. Of course, you can find the decimal to that to see what that means. questions about it. At some point, you would have had to use similarity, so you can't get away from that. If you had ended up with your volume equation down already, you had already used a product rule under it, you had the RDT and the HDT, you could have then gone and found that PR over DT is 1/2 pH over DT, and the substitution there to get rid of the RDT. To me, it's a little easier just to take care of get-go. You don't have to do product rule or anything like that. So any questions about the color? Okay, we'll do Bigfoot tomorrow. Homework. This one is due. Let's make it 6. This one's due on Friday. Okay, for Friday on this one. Tomorrow after this will be a work day. These do take some time to get used to, so definitely start them tonight. Try to get through a couple of them. No, no more AP problems for now.